Hello everyone, welcome to my YouTube channel. Today I am going to discuss thermoelectric effect. It consists of Seebeck effect, Peltier effect and Thomson effect. Join my Telegram group Physics Pradeep to get PDFs of class notes and updates. The link of the Telegram group is given in the description of this video. If you found this helpful, don't hesitate to like, share and subscribe to my YouTube channel for more informative content. We have seen that an electric current through a resistor increases its thermal energy. Also, there are other situations in which an electric current can produce or absorb thermal energy. All these are termed as thermal effect of electric current. Thermoelectric effect refers to the direct transformation of heat into electricity. This technology has applications in the energy conversion, precise temperature measurement and eco-friendly refrigeration. The thermocouple, two wires of different metals joined together at their ends constitute a thermocouple. Here is a copper wire and a iron wire, and they are joined at their two ends and they form a thermocouple. Now the Seebeck effect. When two junctions of a thermocouple are maintained at different temperature, a current is set up in the circuit of the thermocouple. This phenomena is called thermoelectric effect or Seebeck effect. Here two dissimilar metals, that is antimony and copper, and they are connected at their two ends, and one end is at higher temperature, that is hot junction, and another end is at lower temperature, that is at the cold junction. There is a current in the circuit, and this current is called thermoelectric current, and the EMF produced in the circuit is called the thermo EMF. The thermoelectric series or Seebeck series. For given temperature of hot and cold junction, the direction of current in a thermocouple depends on the metals chosen. Metals are arranged in a particular sequence which may be used to predict the direction of current in the temperature range 0 to 100 degrees Celsius. This sequence is known as the thermoelectric series. This series represents basically the thermoelectric series. At the cold junction, the current is from metal coming earlier in the thermoelectric series to the metal coming later in the series. For example, in a antimony and copper thermocouple, the current will flow from antimony to copper in the cold junction. Now the relation between thermo EMF and temperature. The relation between thermo EMF and temperature is given by the relation E equals to AT plus BT square, where E is the thermo EMF and T is the temperature, that is temperature difference between hot and cold junction of the thermocouple. And the variation of thermo EMF is represented by this curve. Here thermo EMF is plotted along y-axis and temperature difference plotted along x-axis, and the slope of this curve represented by dE by dt. The temperature Tn is termed as the neutral temperature. For the hot junction temperature, the value of thermo EMF E is maximum and is called neutral temperature and represented by Tn. For the thermo EMF, E is equal to AT plus BT square, and for T equals to Tn, dE dt will be 0, that is delta E by delta T will be 0. Then Tn equals to minus A by 2B. A and B are two constant. So for a particular thermocouple, the neutral temperature Tn is given by minus A by 2B. Also Tn is given by Tc plus Ti by 2. Here Tc and Ti are the cold junction temperature and inversion temperature of the thermocouple respectively. So what is inversion temperature? Inversion temperature is denoted by Ti, and the temperature at which direction of thermo EMF reverses its direction is called inversion temperature. So here the Ti is the inversion temperature in this graph, and at Ti thermo EMF, basically at Ti particularly thermo EMF E is 0. So for inversion temperature E is 0, and then Ti is minus of A upon B. So remember this formula. Now the thermoelectric power, also it is called as a Seebeck coefficient. The thermoelectric power of a material is a measure of the magnitude of an induced thermoelectric voltage in response to a temperature difference across that material as induced by the Seebeck effect. The SI unit of thermoelectric power is volt or Kelvin. So remember this unit. Thermoelectric power as a unit of volt per Kelvin, and although it is used in the unit of microvolt per Kelvin. If the thermo EMF is given by E equals to AT plus BT square, then thermoelectric power P will be dE by dt, and the expression of thermoelectric power becomes V equals to A plus 2BT. So the thermoelectric or the Seebeck coefficient varies linearly with temperature, and if we plot the thermoelectric power P with the temperature T, then the graph will be like this and the slope of the curve will be 2b. Now the Peltier effect. Suppose the two junctions of a thermocouple are initially at the same temperature and electric current is passed through the circuit by using an external battery. It is observed that heat is produced at one junction and is absorbed at the other junction. Thus one junction is warmed up and the other junction is cooled down due to the current through the junction. So if current is made to flow through a thermocouple by connecting a cell in the circuit, then heat is evolved at one junction and heat is absorbed at the other junction. This phenomenon is mainly known as Peltier effect. If we look at this figure, here two different metals, that is bismuth and copper, is taken and they form a thermocouple and a battery is used. This battery supplies some current, so one of the two junctions becomes cold and another junction becomes hot. So this is the Peltier effect. Now the Peltier coefficient. The Peltier coefficient is the heat evolved or absorbed at the junction per unit current per unit time. That is, heat evolved or heat absorbed at the junction per unit time and per unit current is known as Peltier coefficient. It is generally given by pi and is given by Q by T, where Q is the amount of heat evolved or absorbed at the junction and I is the current and T is the time. SI unit of Peltier coefficient is joule per ampere per second or joule per coulomb. If V be the potential difference at the junction, then pi IT equals to VIT. From it we can find out that pi equals to V, and also from thermodynamics pi equals to absolute temperature into thermo EMF. That is, Peltier coefficient equals to absolute temperature into thermo EMF. As we know, the thermo EMF is given by dE by dt. So Peltier coefficient will be pi equals to T into dE upon dt, where E is the total thermo EMF in the circuit. Now here is two important points. Peltier effect is complementary of the Seebeck effect, and Peltier coefficient depends on the junction temperature. Now the Thomson effect. If a metallic wire has a non-uniform temperature and a current is passed through it, then heat may be absorbed or produced in different sections of the wire. This heat is over and above the joule heat I square RT and is called Thomson heat. The effect itself is called Thomson effect. So Thomson effect is the phenomena of absorption or evolution of heat along a conductor when current passes through it, while one end of the conductor is at hot and another end is at cold. The Thomson coefficient is given by sigma, and if two parts of the metal are at small temperature difference dt, then the electric potential difference dV is proportional to dt and dV equals to sigma into dt, where sigma equals to dV by dt or del V upon del T. The constant sigma is called Thomson coefficient. Here is a table represents the difference between Seebeck effect, Peltier effect and Thomson effect. In case of Seebeck effect, it generates electricity from the temperature difference. Peltier effect basically absorb or releases heat at the junction with current flow. In case of Thomson effect, heat will be absorbed or releases along the conductor with current flow. Seebeck effect converts heat to electricity. Peltier effect converts electricity to heat. Thomson effect converts electrical energy into thermal energy, but not at the junction. Seebeck coefficient is given by del E upon delta T, where del E is the change in thermo EMF and delta T is the change in temperature. Peltier coefficient is given by Q by IT, where Q is the heat evolved or heat absorbed at the junction, I is the current and T is the time. Thomson coefficient sigma is given by del V upon delta T, where del V is the electric potential difference and delta T is the change in temperature. Seebeck effect depends on the material used and temperature gradient. Peltier effect depends on the material used and current in the circuit, and Thomson effect depends on the material used and current. Seebeck effect mainly used two types of materials. In Seebeck effect, two different materials are required in the system. In case of Peltier effect, two different materials are required in the system. But in case of Thomson effect, it requires only one type of material. Uses Seebeck effect used in thermocouple energy harvesting. Peltier effect used in thermoelectric coolers heat pump, Thomson effect used in thermocouple's temperature sensor. Now some important points. In a thermocouple, minimum current flows at the temperature of inversion. Seebeck effect, Peltier effect, Thomson effect, all are reversible process. But Joule's effect is a irreversible process. Peltier heat in a given time is proportional to current flow in the circuit. That is, heat produced due to Peltier effect is proportional to current, directly proportional to current in the circuit, whereas heat produced due to Joule effect is proportional to square of the current. So remember these two terms. Thermocouple should preferably be not used for measuring temperature above the neutral temperature, that is Tn. Thermocouple cannot be acted as AC generator. If we increase the temperature of hot junction, the thermo EMF may be increases or decreases. Thermo EMF is in the order of microvolts. Remember the order of thermo EMF. Thermo EMF is of the order of microvolt. Rate of increase of thermo EMF with temperature at the neutral temperature Tn of the thermocouple is 0. Neutral temperature of thermocouple does not change with the change in the junction temperature. And the last one, the thermo EMF generated in a thermocouple depends upon temperature difference of the two junctions as well as temperature of the cold junction. So if you have any question or queries, feel free to ask me on the comment section of this video. Thank you for watching.